So today we're going to be looking at neutralization reactions and titrations. So this is going to be anytime we react an acid and a base together, basically what happens, how can we calculate what happens, what needs to happen, all that stuff. So first off, for any acid-base reaction that we have, the products are always going to be the same. So anytime that I have an acid and a base react with each other, I'm going to wind up with two different products. I'm going to always wind up with some kind of salt, and I'm going to wind up with water. Now, when I say salt, the technical definition, at least scientifically, of a salt is any ionic compound formed from the reaction between an acid and a base. Normally, when we think of salt, we think of table salt, so sodium chloride, NaCl. But in reality, that's only one of a huge variety of different types of salts that we could have. So while we typically call that salt, because that's usually the only type of salt that we use on a regular basis, that's just one of many different things. So that's one of the things where that's just kind of like a common name, but it is by no means the only kind of salt. So then looking down here at the bottom, we want to identify which one is the acid, which one's the base, and which one is the salt. So for the acid, remember that's the thing. We can either use the Arrhenius definition, which says it starts with an H, or we can use the Bronsted-Lowry definition, which says that it gives away its proton or its hydrogen. So looking at HCl, that looks like it's going to be pretty obviously be the acid just from the Arrhenius. Also, if we go over and we find the chlorine on the other side, we see it's lost its hydrogen, so that's another hint there. So HCl is going to be our acid. NaOH, that's got an OH there, so Arrhenius definition, that is definitely a base. And then when we go over to the other side, so NaCl and H2O. H2O, that's obviously going to be the water. And then NaCl, because it's an ionic compound and it was formed from having an acid and a base react, that's going to be our salt. So for the acid-base reaction stuff, anytime we have them reacting together, the acid and the base are going to be the reactants, and the salt and the water are going to be our products. Okay, so just some quick examples. No need to write these down in your notes, but just to show you the variety of salts that exist. So NaCl, that's typically what we think of as being salt. That's table salt, so you know the stuff that you put on your food and all that good stuff. Definitely edible. You don't want to eat a whole lot of it because, you know, it is kind of toxic for your heart and stuff. Then we've got NaCN, which is sodium cyanide. That's a very deadly poison, so just simply swapping out the chlorine with that polyatomic ion cyanide there, we get basically what's inside those little capsules that you see in like the spy movies and stuff where they've got like the fake tooth, they knock it out, bite down on it, and then it kills them real fast. That's usually what's in those, and it kind of real life that it doesn't take very much at all to do it, so fake tooth is enough to get you. Then KNO3, that's potassium nitrate. It's both fertilizer and it's used in the formation of gunpowder. It's really useful there because whenever you heat up potassium nitrate, it decomposes into potassium nitrite and then also just oxygen. So that's why you can fire a gun underwater, even though there's no oxygen available for it, because gunpowder has potassium nitrate in it. It's able to create its own oxygen, and so it's its own thing. You could also fire a gun in space too. Just fun little fact in case you ever go to space, you need to duel somebody or something. And then sodium fluoride. Prevents tooth decay. So all of these are examples of salts. These could all form from acid-base reactions, but they're obviously very, very different. Okay, so the type of reaction that we get then is going to be a neutralization reaction. So this is a reaction that happens between an acid and a base, and literally anytime you have an acid and a base reacting with each other, regardless of how much there is, what kinds they are, whether they're strong and strong, weak and weak, strong and weak, whatever the combination is, it is always a neutralization reaction because they're always going to try to neutralize each other or cancel each other out. And what it really boils down to is we have our H3O plus ions, and they come in contact with the OH negative ions, and because this is positive, this is negative, they're naturally going to want to attract in the first place. And then because they would much rather form a water molecule instead of those other two things, the OH is going to pull that extra proton from the H3O plus, and it turns into one water. And then because the H3O plus lost one of its protons, it turned into another one. So that's why we've got two H2O over here, not only to balance it, but that's where they physically come from. So again, this is acid because it loses that hydrogen and gives it to the other thing, so that makes it an acid. This is the base because it steals the thing. And of course, you should know by now, anytime you see H3O plus, that's automatically acid. OH minus, that's automatically base. But so for every acid-base reaction, that's the general what's going on behind the scenes. So a titration then is a specific type of neutralization reaction. We typically use this whenever we want to figure out some kind of very specific thing. So maybe we have an unknown sample of something and we want to know like exactly what the concentration of whatever that acid or base is. So we can use a titration in order to do that. So what we'll wind up doing is in this setup over here. So we'll put down in this flask over here whatever our unknown is. So this would be filled with however much of that there is. And then in this thing up here, which is called a burette, we're going to have some kind of solution that we know exactly what it is, what concentration is, all that stuff. So this is probably something that gets made from scratch, or it's ordered from some kind of supply company that's very, very precise in what its concentration is. And so based on how much of your known stuff you have to add to neutralize your unknown, you can calculate using an equation on the next slide or two what exactly the concentration of this was down here. So we know that when we're using this equivalence point, and that's the point where the acid and the base have neutralized each other. So where the amount of acid and bases are the same, or another way to think of it is when the H3O plus and the OH minus concentrations are exactly the same. So the equivalence point is where they have equaled out. It is completely canceled and everything is all hunky-dory and good to go. The end point, however, is where we're actually going to get. So that's where we stop the titration because the equivalence point has been reached. Ideally, the endpoint would be exactly the same as the equivalence. However, for the endpoint, we're going to be using some kind of indicator. So if you remember from the acid-base property slide, there was that huge table that you by no means have to memorize, but it had all of those different colors, those different indicators on there. All of those indicators would be useful based on what kind of acid and base neutralization thing we're going for. So you'd pick which indicator you're looking for, you would add however much of whatever your known was to your unknown, and based on that indicator color, you'd be able to tell the pH, which tells you when your endpoint, which would hopefully tell you your equivalence. So you want to try to pick one that would be as close to the equivalence as possible, but A, it may not be possible to hit one straight on, and then B, even if you do, if you remember those had a range on them, and this is a lot of human error, so this endpoint, while it's going to be really close, is usually not going to be exactly the same as the equivalence. So just a heads up there. And then also, like I said, because this is between an acidic and a basic solution, if your unknown is an acid, that means you're going to be titrating it with a base up here. And vice versa. If your unknown is a base, you're going to be titrating it with an acid. Okay, so then we get these titration curves. And you'll want to kind of jot down the general shape of these. You don't have to sit here and label out every pH and every volume of stuff added. As long as you get the general shape and then where the endpoint is, you're going to be good. So strong acid, strong base. You could think of this as these curves as being kind of like a tug of war. So remember, a pH below 7 is acidic, pH above 7 is basic. So if I have two strong things pulling in a tug of war, they're going to be equally matched. So I would expect the flag to stay, right in the middle of the rope, or right in the middle of the field, whatever you want to call it. So the endpoint in a strong acid, strong base titration, it's going to be smack dab in the middle at a pH of 7, because they're both going to balance out. We can also tell that this is a strong acid, strong base, because the first word in the thing is going to be what our unknown is. So our strong acid is what we're starting with, and then we're adding a base to it. And you can tell that in two different ways. One, if you look at the label down here, you can see this is milliliters of NaOH. So that's obviously going to be a base. So that means we're adding a base, so we're starting with an acid. The other way, and probably in my opinion, the easier way, is if you look, the pH we're starting with is 1, that's definitely an acid, so that means we're starting with an acid. So you got a couple different ways of remembering it. But the first word is always what we're starting with. So there was some unknown strong acid that we're trying to figure out the concentration of. So we added this NaOH that had a molarity of 0.1 molar to figure it out. So again, strong and strong are going to completely cancel out. So weak acid, strong base then. So the curve looks a little different. So if you notice, it doesn't have like that same kind of loopy curve like that. It actually kind of jumps up quick and then sort of takes that shape. But the big important thing is that the endpoint here is actually going to be above 7. Because if I'm doing this weak acid, strong base, think tug of war, that base is going to win. So that means that the endpoint is somewhere above 7. You won't need to know exactly where above it, just as long as you know whether it's above, at, or below 7. That's all we need to know. So the endpoint's above 7. And again, the weak acid is what we're starting with because we do have a pH lower than 7. Even though it's not as low as before, it is still definitely an acid. And then we're adding a base to it because this pH keeps going up and up and up the whole time. Strong base, strong acid. Same sort of thing there, except now it's going to be flipped. So now I can tell that I'm starting with a base because A, it said strong base, and then also the pH started out really high, above 7. So that means we're starting with a strong base, adding a strong acid, and again, we have two strong things. They're going to equal out in our tug of war game. So we would expect the endpoint to be right at 7. And then just something to keep in mind, for whatever reason, like 90% of the time, they're going to be acid-base titrations, meaning that we have our unknown acid, we're adding a base to it the whole time. But for the other 10% of the time, they could be base-acid titrations, where we're starting with a base and then adding an acid to it. So this is one of those cases. So it doesn't always increase from left to right. Sometimes it can decrease as we go that way. Just depends on what's happening, whether we're starting with the acid or we're starting with the base. All right, and then strong acid, weak base. Again, started with an acid, we would expect the acid to win because it's strong, so therefore endpoint is below 7. Okay, so the actual titration then. So this is used to find the concentration of an unknown solution. And we're going to use this equation here. And it's a lot simpler than it probably looks. But in order to do a titration, we have to know the concentration of one of those two solutions, which is called the standard. So the standard, it's called the standard because it's been through a standardized process to say this is exactly this concentration and all this other stuff. So this equation, and again, you will need to know it, but it is pretty simple. So each side has molarity, each side has volume. That's what the capital M is. Remember, capital M is molarity. Capital V here is volume. And then there's just this number of either H plus or OH minus. So what the molarity and the volumes are pretty straightforward. Molarity is going to be measured in molarity or moles per liter. The volume can be measured in whatever volume units you want, as long as it's the same on each side. So if this one is milliliters, this one can also be milliliters. You could have one of them be liters and the other one liters too. You just can't have a mix. So if you have one of them milliliters, one of them liters, you got to convert one to the other. If you want to play it safe and always go to liters, because I know some of you did that when we were doing gases, you're more than welcome to do that. It's just another little extra step, but if it makes you more comfortable, by all means, go for it. So the only quote-unquote complicated part of this is going to be the number of hydrogens or the number of hydroxides. And this tends to be the thing that a lot of people forget. So if I'm looking at an acid, let's say I'm starting with HCl. This number of H plus is literally just how many hydrogens are going to pop out of this acid when it dissolves. So this has one hydrogen, so in that case, our number of H pluses would be 1. For sulfuric acid, H2SO4, I have 2 hydrogens, so it's going to be 2. For phosphoric acid, I've got 3 of them, so H plus would be 3. Then for OH minus, it's the same thing. NaOH, that's going to be 1. Ca, OH2, that would be 2. And then if I had something else that was a 3, that would also be a 3 there. So don't overcomplicate the number of H plus and number of OH minus. because it's literally just how many of those things are there in the chemical formula. Just make sure that you go through the effort of crisscrossing if you're just given like the name of an acid or a base instead of the actual formula. And then also just being careful not to forget it, because that's generally where people mess up on this, is they forget to put it. They just do molarity times volume on each side and call it a day. Okay, so first example. So I've got a titration. I'm trying to titrate a sample of 0.31 molar HNO3, and in order to do that, it took 75 milliliters of a 0.24 molar potassium hydroxide solution in order to reach a pH of 7. And so I want to know the volume, the original volume of this sample. So I don't know, maybe I found a cup or something like that sitting around, and I wanted to be very accurate, so I didn't want to like pour it into something, because then there's still going to be the droplets left in the cup and all that stuff. So we could use a titration at this point to figure out exactly what's going to happen. So pH of 7, I've got a strong base and a strong acid here, so I know that that's where the endpoint is, so that's where they're equal. So once it hits there, I know it's good to go. So I'm going to use my equation, molarity of my acid times the volume of my acid times the number of H plus, or H3O plus, whichever way you want to look at it, equals the molarity of my base times the volume of my base times the number of OH minus. And so we just plug stuff in, just making sure that units are good. So for the acid, so I know that's 0.31 molar, so I can go ahead and put 0.31 molar in there, times the volume of the acid. So I don't know what that is. Be careful, it's not the 75, because that's attached, because saying 75 milliliters of my potassium hydroxide. Also, we were looking for what is the volume of the sample that we had, and the sample was that, so it makes sense that we don't know our volume yet. And then number of hydrogens. So I look HNO3, it's only got one H in the formula, so that's just going to be a 1. Equals, so molarity of our base, which is going to be 0.24, times the volume of our base, that's going to be 75 milliliters. And then the number of OH, so in KOH, I've only got one OH there, so that is also just going to be a 1. So when I go to do that math, so this side, 0.31 times VA, and of course the 1 just kind of goes away, because anything times 1 is that, equals those two, this was still molar, stick that in there. So this is 18, if I do that times that, that's molar times milliliters, so they're just still there, then times 1. I can tell my molarity on each side cancels, because I have 1 there. I could have canceled it up here too. It's a little easier to see here. So all I have to do to solve for volume then is divide by 0.31. So the volume of my acid should come out to be 58.1 milliliters. And that would make sense that it's still going to be milliliters, because it's going to be volume. And the only thing that matters is that it matches each side. So if you wanted to convert this to liters instead, that would be like 0.075 liters. Your answer would be like 0.0581 liters. Doesn't matter, as long as it's the same on each side. So if you start with milliliters, you're solving for volume, you're going to come out with mils. Alright, go ahead and give this one a shot, and pause it real quick so you can work it out yourself. Alright, so again, molarity of acid, volume of acid, number of H plus, equals molarity of base, volume of base, number of OH minus. Alright, so molarity of my acid. So I see this 29.5 milliliters of 0.15 molar NaOH, so that's all together. And it's neutralizing 25 mils of a diprotic solution, and I want to know the concentration of it. So the molarity of my acid then, I don't know, because I'm looking for concentration. So molarity of the acid. How much acid did we have? It looks like 25 milliliters. Alright, then for number of hydrogen. So this said it was a diprotic solution, so we don't know the exact formula, But remember, if something is diprotic, that means that there are 2 hydrogens in its formula. So I'm going to throw a 2 there. Equals molarity of the base. So that is... my molarity is 0.15 molar. Times our volume, 29.5 milliliters. And then number of OHs. An AOH just has 1 there. So we've got that 1. So molarity times 50 milliliters, because 2 times 25. The other side is going to be 4.425 molar milliliters. Have milliliters on each side, so this cancel out. Divide each side by 50, so the molarity of our acid then is going to be 0.089 molar. And there we go. That is it.